şeyden bahsedeyim. More on identification. Let me just, talk about examples. For example, take any interval like this and glue, so divide this into the following relation, where, so we identify only 0 and 1. So this is an equivalence relation, and it is the following relation. Any point inside the interval is not identified to anything. So each equivalence class is a single point, but the endpoints are identified. Therefore, the equivalence class containing one boundary point contains the other one. So one of the equivalence classes has 2 points, but all others are 1 point. So you just divide this space into this relation. And what is the result? Of course, the result is just you glue this point to this point. So you just get circle, okay? And you can actually write down a map. So suppose this is X, okay, 0, 1. And then you divide this into this relation and you just get, ya da şöyle diyeyim. Here you have X divided by this relation, and this is our, let's say, Z circle. What is this map? Let's say F is just the map. F of T is just cosine 2 pi T sine 2 pi T. Okay. This map is continuous and it respects this relation. Why is that? Because you see 0 and 1 are mapped to the same point. Therefore, this map descends to the quotient and gives us a map F bar. And although F is not 1-to-1, this map is 1-to-1 onto, since this is continuous, this is also continuous. And actually, it's a homeomorphism. Okay, so F bar is a homeomorphism. You can check that it's a homeomorphism. It's not difficult. So the quotient of this space with this relation is just circle. Of course, you may regard this quotient space as also follows. So this is 0, 1 divided by this relation, or you may regard this as follows. This is just real line divided by integers. What we mean here with this is the following. Here, this means you identify any real number with x plus n, where n is an integer. Actually, this is this corresponds also the following. This is an Abelian group. This is a subgroup, and you just take the quotient group. Okay, you may also consider this way, and this thing actually is also an Abelian group. The quotient, it is the circle. What is the group operation here? You may consider this as unit complex numbers, and here it is just the multiplication map. actually, you know, you have this map R from, so you have this map, you take this and send it to cosine 2 pi t sine 2 pi t, or you may regard this as a complex number, and this is just 2 pi I t, okay? So it's just exponential map, and let me say this map is just F. So this is a group homomorphism. Group homomorphism. Here addition is the operation, here multiplication is the operation, and exponential map sends addition operation to multiplication, right? Group homomorphism with what is kernel of F? Kernel of F is the points where this is equal to identity element, which is 1. This is 1 only if t is an integer. So the kernel is just the set of integers. Therefore, S1 as a group is isomorphic to, right? R divided by kernel F. So it is just R divided by Z. Okay. So it's a quotient both algebraically and topologically. What you can do, you can just generalize this. So consider this map now from R2 into S1 sharp S1. So what is this map? F of xy is just e to the power 2 pi ix, e to the power 2 pi iy. What is the kernel of this map? Kernel of F is just the set of points where this is mapped to 1, 1. So this is an abelian group, product is an abelian group, and this is the identity element. And what is the kernel? Both of them should be identity. For these to be identity, x and y should be integers. So both x and y should be integers. And this gives me what? R2 divided by Z2 is isomorphic to S1 times S1. Okay. Of course, topologically, S1 times S1 is just, what is this? This is just, you take a circle and you actually have S1 copies of the circle. So S1 times S1. So you take a circle in space and then just rotate it along a circle. What you get is, of course, a torus like this, right? You have this circle, and then you just carry the circle over the center circle. Let me just describe this topologically also. So this relation corresponds to what? You see, in the plane, any point xy is identified with any point x comma n, y comma m, right? 2 points are identified if the difference is an integer. Here m and n are integers. So I want to draw the picture of the quotient, right? This point is identified with this one for any m and n. What is the quotient space? Well, what we see is this. Take the unit square here. unit square. Any point in the plane, right? By just taking integer parts of the coordinates, you obtain a representative here. Okay, so any point in the plane has a representative in the unit square. Değil mi? Mesela diyelim ki x, y şu nokta olsun. 172.8 eksi 18.91. Bu nokta neye eşit? This is equivalent to what? Take the integer part. So this is equivalent to this, and then bu da 19 eklersen buna 0.09 mu eder? So this point is equivalent to this point, and it's a point somewhere here, right? Somewhere here. Belki şurada. So every point in the plane has a representative. Therefore, if I want to draw the picture of this quotient space, I can just concentrate on the unit square because every point has a representative on this unit square. But then we have further identifications. What are they? So if you have any point here which has coordinate 0, y, this point is identified with this one, 1, y, right? So I have to identify this point with this one and identify this point with this one. Therefore, I have to identify this edge with this edge, right? Like this. And we represent it by putting an arrow like this, okay? So I identify this edge with this edge. Further, if you have any point here, let's say x, 0, this point will be identified with this one, x, 1. And again, this point will be identified this one with this one. Therefore, you have to identify this edge. Let me draw it like this, so that you know this is different than this one. So this edge should be identified with this one. So let me draw that picture again here. We have a rectangular piece of plane, and this edge will be identified with this one, and this edge will identified with this one, and no other points on this rectangular region are identified. For example, this point will not be identified with another point, but the boundary points are identified like this. All right, let me identify this edge with this edge, right? When you identify this edge with this edge, this is what you will get. You will get a cylinder, right? Something like this. Belki şöyle çizmekte fayda var. Right? And still, this edge needs to be identified, this one. So these two edges are identified, and it is, let's say, this one, right? That common edge. And still, I need to identify this circle with this circle. And you can do this. You just, bend it like this and then glue, right? When you identify with this two, you just get something like this. So these two edges are identified like this. You have the circle, and you have also this circle. So what you get is a torus. Okay? Şuraya koymuştum. So this way we obtain surfaces, and actually all the surfaces can be obtained this way. İsterseniz şunu da yapayım. Ona 1 dedim, buna 2 dedim. 3, şunu söyleyeyim. Higher genus surfaces. All surfaces, compact surfaces are, sphere, torus with 2 holes, and so on. Torus with n holes, 1, 2, G. We say that this is an orientable surface of genus G. Orientable surface of genus G. All orientable surfaces, compact surfaces are these, okay? And then we have non-orientable ones like RP2, Klein bottle, so non-orientable ones. Surfaces, RP2. I cannot draw its picture. We described it, but it's not easy to draw. But Klein bottle, I can draw it. Of course, this Klein bottle also doesn't embed into R3, but it is immersed into R3, so we can draw a picture of it. And it's like this. So we have a bottle like this. But, this bottle goes like this. So we have a neck also, and this neck just cuts itself, and so, okay. Yani şişenin boynu içine giriyor, sonra da dibine yapışıyor. Tamam mı? Tabii bu R3 içinde oturmuyor çünkü kendisini kesiyor. Ama R4 içine kendisini kesmeyecek şekilde şey yapılabilir. Burak'ta bunun camdan yapılmışı var. Hatta içine su koyabiliyorsun. Koyabiliyorsunuz ve dökülmüyor. Yani aslında bunun içi dışı yok. Değil mi? Çünkü şurası dışarıdaki bir nokta, ama bunu alıp şöyle getirdiğinizde içine giriyorsunuz, ama bir şekilde içine koyduğunuz sıvı böyle hani çevirin, dökülmüyor. Okay. Şeyi söyleyecektim. Mesela şöyle bir surface nasıl elde ederiz? Let me just describe how you can obtain genus G surface. Actually, it is enough to explain just this. You may obtain this by so-called connected sum operation. So we take torus. Here, what we mean by torus, this is just circle times circle, okay, torus. We have 2 copies of the torus. We take connected sum, and what we get is genus 2 surface. What we mean by connected sum is this. So you have a torus, you have another torus. With connected sum, we mean the following. You take a point here, take a point here, and then just delete a neighborhood of this point. So when you delete a neighborhood of this point, you get disk like this. So a disk is removed. Yani oradan noktanın bir komşuluğunu çıkartıp atıyorsunuz. 2 tane delik oluştu. Ondan sonra da you just glue this two boundary circles, right? You just glue them, this point with this one with this one. So when you glue them, you just glue them along their boundary. So what you get is just, of course, something like this. So you just glue them. And what is this? This is just the genus 2 surface. Okay. So all the orientable surfaces can be obtained like this. And we can actually regard this surface, as in the case of torus, as an identification of a plane region. How? You see, this torus was this, right? Let me say, this one torus is this one, right? This is a torus. When you identify this edge with this one with this one, you get this torus. Take 2 copies of the torus. Aslında şöyle diyeyim, şuna ya da şöyle, bu tamam, şöyle kalsın. Şunlara isimler vereyim. Şu A, B, B olsun. Şu C, D. Yani D diyorum çünkü bunların ikisi yapıştığı için tek bir tane olacak. Burada da A ile A, B ile B yapışacak. Bunları peki yapıştırırken ne yapıyorum? So to glue this, first I have to delete some balls. So let me just do it this way. Take a ball like this and take a ball like this and delete them. Bunların içini delete edin. Yani şurayı delete edersem şu noktayı da şöyle açayım. O zaman şöyle bir şey elde edeceğim. Şöyle diyeyim. Şurası B, A. Şurası da C olsun. Şöyle. Şurada da yok C demeyeyim de ona E diyelim. E diyeyim. Ondan sonra şurada da benzer bir şey var. Şurası D, C. Şurada da buna da E kenarı diyeyim. Bu ikisini de yapıştıracağım. Bu ikisini yapıştırırsak ne elde ederiz? Yani bu işte şu circle'ları yapıştırıyorum. I just glue these circles. So let's do that. So when you do that, you will get something like this. This edge is identified with this one. And how many sides we will have? I will have 4 sides here because this is identified with this one, and 4 sides here. So I have 8 edges. You may consider them like this. So this is the common edge, E. And then if this is E, so this is C. And then I have D. And then we have C. I have D. And then here, this is A. This is B. This is A, and this is B. Something like this. So it's like, yani bunları tekrar şey yapsam şöyle düşünebilirim. Rename etsek şöyle A rename ettiğimi düşünün. Şurası B. Şu A'nın tersi şöyle diyeyim. A inverse diyeyim. Çünkü tersten gidiyor. Bu da bunun tersi. B inverse. Şurası C. Burası, buna da D diyelim. D. Burası bunun tersi. Değil mi? C inverse. Bu da bunun tersi. D inverse. Yani şöyle bir şey oluşuyor. Şuradan başlıyorsunuz. Sekizgen var. So you have an octagon and sides are like this. A, B, A inverse, B inverse, C, D, C inverse, D inverse. Okay. A, B, A inverse, B inverse, C, D, C inverse, D inverse. Okay. And for the torus, what was it? That thing will be important soon. Okay. So this identifications using these letters. For the torus, we will have something like this. So we had A, sorry, and let's say B and B. So if you go like this, you read this as A, and then B, and then this is A inverse, and this is B inverse. Okay. And for genus 2, we have this word. A, B, A inverse, B inverse, C, D, C inverse, D inverse. Okay. Peki. Benim notlarda daha şey var. Daha detaylı bunlar yazıyor. Onlara da bakabilirsiniz. So for two-dimensional, objects, in this case surfaces, we have, tools like this. We can describe them in, several ways. Quotients of a plane piece or quotient of two surfaces, glued along some boundaries and so on. In higher dimensions, there are similar techniques, but except surfaces, the higher dimensional objects are not understood like surfaces. We know all the surfaces. We have full classification. We know many things about surfaces, but for even three-dimensional manifolds, we know a lot of things, but there are also a lot of things which we don't know. And in dimension 4, things are even worse. Things get very complicated. So dimension 2 is actually the only dimension, non-trivial dimension, which we know all the surfaces, okay? All the objects. Yani surface'ların dışındaki diğer manifoldlar hakkında çok şey bilmemize rağmen elimizde bir classification falan yok. Sadece yani 3 boyutta da classification var ama hani orada anlaşılmayan hala bir sürü şey var. 4 boyuttaysa işler daha da karmaşık. Ama hayatınızı surface'larla geçirebilirsiniz. Yani surface'larda bile hala çalışılan bir sürü problem var. Bizde işte Mustafa Hoca, Mustafa Korkmaz o surface'ların uzmanıdır. Şimdi we will talk about groups. So far we talked about topological spaces. Now we will associate to each topological space a group, so-called fundamental group. But first we need to define some notions. The first one is homotopy. Why do we, try to associate algebraic objects to geometric objects or topological objects? Because studying topological objects is usually more difficult. You cannot compare them, okay, easily. You can compare groups. You can just realize that one group is abelian and the other one is not abelian, or they may have different orders. Algebraic objects are comparatively more easier to compare with respect to topological things. For example, how can you show that sphere and torus are not homeomorphic, right? Things from analysis courses is not enough to distinguish them. They are both compact. They are both connected spaces. Yeah, but those considerations, you have to prove several things. It's not that easy. So you say there are integrals, line integrals, which doesn't give you 0, but on the torus, they will all give you 0. But that needs the construction of actually de Rham cohomology, Meyer-Vieux torus sequence, and so on, a lot of work. So it's not that easy. But it is one way, using differential forms and integration and so on. Another way, you may associate groups to these gadgets, but that's not also, is something easy. And we will show that, this has trivial fundamental group, while this one has fundamental group Z plus Z. And since they are not the same, we will say that these two spaces are not homeomorphic. That's another formulation of what you have said, actually. That's why, we will, so that's one reason why we associate algebraic objects to topological objects. And this study in general is known as algebraic topology, okay? So here is the definition of what a topology is. Let's say these two be two continuous maps of topological spaces. We say that F and G are homotopic maps if there is a continuous map. The continuous map map H defined on X cross I. So on the product topology, here I have the space X, and here this is the interval I. So I is just the interval 0, 1, considered as a subspace of R. So the topology on 0, 1 is just the topology inherited from the real line. Okay. And we ask that this H satisfies the following. So that H x comma 0 is equal to f of x, and H x comma 1 is g of x for all x in x. We denoted, we picture this as follows. We say our homotopy is this H, and here this is the product space X, and this is the interval 0, 1. And then we do the following. A point here is just X comma 0. A point here is just X comma 1. Okay, this is the interval 0, 1. And we say that this is F, so restriction of H with respect to X comma 0 is equal to F, and this is just G. Okay, so this picture tells us that the map F and G are homotopic maps. Okay, here it is important that you ask H to be continuous on this whole space, okay, on X cross Y. Ya bu ne demek? So this means that you have two maps F and G from a space into another, and these two maps are connected to each other via continuous maps. So at each step you have a continuous map, but actually it is little more than that. Not only all these levels are continuous, but the whole map is continuous. It is more than saying that at each level X cross T, this map is continuous. It is more than that, actually. Okay. Şeyden bahsetmişim ama gerçi burada pek zaman kalmamış. Bahsetsem mi? Okay, so next time maybe I'll talk about so-called rotation number. rotation number. This is a homotopy invariant. So it's invariant under homotopies. And what's the rotation number? Let me just say a couple things. Suppose you have an immersion. What we mean by any immersion, it is not a one-to-one map, but its derivative is always one-to-one. So it corresponds to the following. You have this circle. You have the circle. And its image is something like this. So at each point, you have this tangent direction. And let's say this point here is mapped to this point. And this tangent vector is mapped to here. The way we just say that its derivative at any point is not zero. Yani şey diye görebilirsiniz immersion'ı. Bu nesne üzerinde motosikletle gidiyorsunuz ama hiç durmayacaksınız. Tamam mı? Hiç durmadan gidebiliyorsanız o zaman işte bir immersion veriyor. Yani hızınız hiçbir zaman sıfır olmayacak. Dolayısıyla mesela şöyle bir şey yapamazsınız. Değil mi? Motosikletle şöyle gidemezsiniz. Hani buraya geldiniz, bir anda geri gideceksiniz. Havada takla atarsanız olur da. Gerçekten takla atarak bunun denklemini yazabilirsiniz. Yani havada bir takla atarsanız hiç durmadan geri gidebilirsiniz. Tabii çok tavsiye edilecek bir şey değil yani. Evde denemeyin. Okay, so next time let me just talk about this immersion and its relation to homotopy. Okay. All right, let me just stop. Kaydı durdur. Tamam.